firstly, I would like to thank the organizing committee for giving me the opportunity to present my work. I am Rajat Saxena from the Interdisciplinary School of Science, Savitri Bai Phule, Pune University. I graduated 2 weeks ago, and I will be presenting my bachelor thesis that was under the guidance of Dr. Deepak Dhar at Indian Institute of Science Education and Research, Pune, IISER-Pune. Uh, and the topic of my thesis was simulation of magnetization in ferromagnetic material using the random field Ising model. So this will be my basic layout of the talk. And with this, let's dive right in. So what we all have seen this hysteresis loop in our undergraduation physics lab where we find this on an oscilloscope, where we see this on an oscilloscope for various ferromagnetic material, where this half of the curve is the magnetization and this half is the demagnetization. And what we see is a very continuous and a smooth looking curve. But in reality, this curve is actually full of these discrete jumps and discontinuities. So you can see this smooth curve if you zoom in and you will see it is somewhat like this. And this is because of neighbor-neighbor interactions, random domain orientations, and material impurities or defects. And due to this, the domains that flip, it happens irregularly, and we get a jerky change in the magnetic state. And these jumps are not seen in our normal oscilloscopes because these are very high frequency and they're beyond the bandwidth of our standard oscilloscopes. So my goal was to model this, I mean, simulate this. And what I used for this was a version of the Ising model. So in very simple terms, Ising model consists of magnetic moments. The classical Ising model consists of magnetic moments which can only point in two directions, up or down. And if it's up, it's +1, and if it's down, it's -1. And these magnetic moments are arranged on a lattice. This lattice can be 1D, 2D, or 3D. And it can be any lattice, cubic or monoclinic, trigonal, anything depends on us. For my case, it was 1D lattice, 1D square lattice. So yeah, and what happens is these magnetic moments interact with their nearest neighbors, that is just exact neighbors, and with the external field or temperature that we apply. And this entire model or these entire domains go under a phase transition at certain critical temperature at which these spins will align in a particular direction such that their energy becomes minimized. So that will be their equilibrium state. So this was first proposed by William Lenz, and this was pursued by his PhD student. His name was Ising, and after him, it's named as the Ising model. So what I used was a special version of the Ising model, which is called as the zero temperature random field Ising model. So it is a version wherein we conduct things at zero temperature and at random field. So here the zero temperature means that it happens at a constant temperature and there are no thermal fluctuations as such. So that's why it's called as a zero temperature. And the random field because the lattice that I showed you earlier, each lattice site we will introduce a random field, and that random field will be given by this Gaussian distribution. And that's why this is called as a zero temperature random field Ising model. And this model is defined by this Hamiltonian. So we don't need to worry much about the Hamiltonian. I'll just explain what the terms are, and then we'll see why we don't need to worry about the Hamiltonian. Here, J is a coupling constant. We choose the unit such that this J becomes 1. Si is the spin at the ith state, and Si plus 1 is obviously the neighboring state. And h of t is the time varying external field that I'm going to apply. And hi is the random field that is given by this distribution, and Si is the spin of the ith state. So Si will have two values, +1 or -1. Hi will depend on distribution, and h of t will depend on me. So I can choose whatever. So yeah, now I'll explain why this Hamiltonian is not important for my work, because this Hamiltonian would be important if we would be solving it through mean field theory or some other analytical technique. But what we are going to do is a numerical simulation. So what is for us, what is more important is this net field at each site. So this is given by this relation, which is the terms are exactly the same as we saw earlier, where Sj are the neighboring spins of the ith state. So if you are at the ith site, the Sj will be the both of the neighbors. So yeah, so this is what, so what we do is we calculate this value for each site, and when this H effective changes sign, or it becomes positive, that's when we flip a spin. So this is what we do in the entire process. So a spin can flip, it has two possibilities of flipping. One where where there's an increase in the external field and it flips because of that, or because one of its neighbor flipped. So because of neighbor interaction, it can flip. So these are the two things that can lead a spin flip. And obviously, once we know the once we know the random field of all sites, all spins will flip deterministically. So with this, I'll quickly discuss. Yeah, this is a pictorial representation of what I was saying. So these are all. So I start with a condition where all spins are pointing down, and these are the neighbor interactions. So you can see, because it has open boundary conditions, so the edges have -1 and -1. However, the inner terms have -2. So when I apply an external field of 1 with some arbitrary units, you can see certain fields, and here is the random field. So the spins that have the uh, positive local field will flip. So all the red arrows are the ones that will flip, and the yellow ones are the ones that will flip because of the neighbors. So this is how this model propagates. So this is a basic simulation algorithm. So I initialize with all spins pointing down. Then I slowly increase the magnetic field. And so I have to very carefully choose the magnetic field here. I need to be at a very good resolution so that I get the jumps that I was showing earlier. And then using equation 3, that is this, I will calculate the spin at each side, the net field at each side, and which are positive, I will flip them. And then once this is done, I'll recalculate the effective magnetic field at each side and flip, and considering that some spins have already flipped, and we will then flip the neighbors of it if they have a positive field. Then I'll repeat this step 3 and 4 till all spins have flipped for that external magnetic field. And or what we can say, that system is saturated for that particular field. And then I'll break the loop, and then I'll increase the external field. And this will continue till the entire system is magnetized. So this simulation was done on in Python using Python libraries like NumPy and Matplotlib. Very simple. This simulation takes the one I made. It's a 1D model, because when you increase the dimensions of the model, the computational time drastically increases. So what we have is, this is just an example plot from my work. So this is how the magnetization curve looks like. So this might be very familiar to everyone. So this is the magnetization part of it, and you can very clearly see the jumps here, and some bigger jumps can be seen here as well. So this model, this plot is, it's specifically for r equals to 3.1, or the standard deviation of the Gaussian that was used to make the random field. That is r equals to that is 3.1, and the jumps, as I said, are apparent. And such a simulation of this size. So this is for lattice size of 1,000 spins. This approximately takes 2.3 minutes on my computer, uh, which has certain specifications that I don't recollect. But yeah, so this, all the work that I'm going to show ahead is done on my own personal computer. I didn't get time on the supercomputer at IISER, the Param Brahma computer. They didn't give me time. So whatever I'm going to show ahead, it is on the output of my computer, and it roughly takes, so 1,000 spins is ideally a very small number to get a good output. So I work with 10,000 spins or 10,000 lattice sites, and because of that, it takes up to 8 hours to run one to run the entire program once. So it takes, so for me it took approximately 150 hours to complete just the simulation part to get the output of it. So I hope you guys enjoy the plots that come ahead. Yeah. So this is how when we change the number of lattice sites, how does the magnetization curve changes? So what you can see is with change as when the n is very small, the jumps are very big and magnetization happens very quickly. However, as you increase n, the number of jumps increase. So here you can see there are like 1, 2, 3, 4 jumps. Here the jumps is obviously more than 4. It's even larger here. And for this, it would be very large, obviously. So as you can see. So what we can see with increase in n, the number of jumps also increase. And also you can see a curve-like formation. So this happens because if when you consider, oh, and by the way, this magnetization is magnetization per spin. So we calculate the net magnetization divided by the lattice site, the number of lattice sites. So when you have only 10 spins, even if two of them flip, that is 20% of the entire lattice. So that's why even if two spins flip, it gives a big jump. However, when you have 1,000 spins and two of them flip, that accounts for 0.02%. Hence, the jump is very, very small. So that's the logic behind the jump size here. Moving on to change in R. So as you can see, as you increase change R, you can see it's from R as R equals to 0 to R equals to 4. You can see how does the magnetization curve changes. An interesting result is for R equals to 0, wherein the random field is 0 at each side. So this system ideally behaves like a switch. So when an external field is applied, when the second the external field becomes positive, the entire system will instantly magnetize in one big jump. So that's what is being shown here. Um, and what other thing that it's for some it might be very obvious, but I found it very fascinating. And the point is the positive half of the Gaussian, it accelerates the process of magnetization. As you can see, for R equals to 4, that's the highest standard deviation. The magnetization starts at even very low values of external field. However, for lower values like R equals to 1, it happens very late. Now, so the positive half of the Gaussian accelerates the magnetization process. However, the negative half of the Gaussian slows it down. What you can see, the material that starts magnetizing very fast. So this is starting to magnetize, but it fully magnetizes or saturates very late. So this is what the positive half of the Gaussian and the negative half of the Gaussian have an effect on the curve. So just to prove my point, or just for simplicity, I have two curves. One has a random field with the Gaussian distribution, and one has with an exponential distribution. So as you know, exponential distribution will be non-zero. So as you can see, it's from 0 to up to 10. So you can see magnetization starts it starts, but there is no slowing down. So it instantly magnetizes. There is no slowing down of the curve. However, the positive half will accelerate, but the negative half will slow it down. So that's the difference between the two plots. And just to prove my point, how these two, what does the negative half of the Gaussian do? Moving on to what is the effect of R on maximum jumps. So max jump is basically the highest jump or magnitude of jump that is there. So this can be calculated by doing the subtraction of neighboring data points and getting the highest of those. And you can see it increases exponentially. And yeah, so for this I had to get there are almost I think 11 data points, each with the plot size equals to the lattice size equals to 10,000 and averaged over 10 iterations. So the runtime for this was 110 hours. That is approximately 4.583 days. So this is how long I took just to get this one plot. So yeah, so this was just for, I say, a factoid. Yeah, so this is the same curve as a earlier one, but here we have for two values. The blue one is for n equals to 10,000 and the yellow one is for n equals to 1,000. So you can see how does these curves also vary with n. So yeah, so moving on to magnetize. Yeah, so obviously as I said, the Gaussian distribution, we can choose any other distribution for the random field. So here I have chosen uniform distribution, binomial, and exponential. I had already shown. So for uniform, as you can see, it just gives the signal 1. So at exactly 0, the system will magnetize. And for the binomial distribution, you can see it is positive, but it is drastically varying, and it's giving very high values of random field at each site. Hence, the system will again magnetize in very big, huge jumps because the random field is very high. So this is how you can see what is the effect of different distributions on the magnetization curve, and why using the Gaussian distribution is very good. Good is a good word to use. So it's very good to use a Gaussian distribution because we get what we expect. Yeah, so a philosophical conclusion from this is nature does things in a very beautiful and effortless way, but when we humans try to understand and recreate these natural processes, it gets very complicated and time consuming. So the simulation that you saw, I did this during the end of my project. Before that, I was just reviewing literature. So within 2 months, I had to make the simulation and get those output plots. So yeah, that's why it got pretty complicated and time consuming. And these are a few references. So my thesis is now available on ResearchGate, and the simulation code is made public on GitHub. So you guys can have a look. And with that, thank you. So this is my picture with Dr. Deepak Dhar. So by the end of my project, he had shifted to ICTS Bangalore. So this is the only picture we have, an online picture. And this is a picture from the IISER main building where I worked for a year. So yeah, thank you. And if you have any questions, I would love to take those.
Thank you, Rajat.